The atom is not the smallest thing. It never was. And the person who drew that diagram on your classroom chalkboard knew it. They taught you a model that was already wrong when it was invented, because the correct version is harder to draw. That's the calculation they made. Simplicity over accuracy. And most people never find out. I'm Marie Curie. I did not learn about radioactivity from a textbook. I watched it happen in a cold laboratory in Paris, with instruments I built myself, measuring something I could not yet name. The atoms in my samples were coming apart. I didn't cause it. I couldn't stop it. It was happening on its own, by rules I didn't yet understand. So when I tell you what's actually inside an atom, I'm not reciting a chapter. I'm telling you what the evidence forced me to accept, piece by piece, even when it made no sense. Scale. We need to establish scale before anything else. If you took a single atom and expanded it to the size of a football stadium, the entire structure, the electron cloud, everything, the nucleus at the center, would be the size of a housefly. One housefly in the middle of a football stadium, and everything between that housefly and the outer walls empty. Not mostly empty. Empty. That space is not nothing. It contains the electron cloud, and we'll come back to that. But there is no solid matter filling it. The atom you were shown in school, that satisfying little sphere with rings around it, is almost entirely absent. I carried radioactive material in my coat pocket for years. I could not feel it. I could not see it. It was dismantling itself, atom by atom, continuously, and I had no physical sensation of it whatsoever. That's how small this is. That's how invisible the interior of matter is to everything except the right instruments. Now, the nucleus, that housefly at the center of the stadium. Two types of particles live there. Protons and neutrons. Protons carry positive electrical charge. Neutrons carry none. The number of protons is what makes an element what it is, not its weight, not its color, not how it behaves chemically, just the proton count. Hydrogen has 1, carbon has 6, uranium has 92. Change that number by even 1, and you have a completely different element, not a variant, a different substance entirely. Neutrons are the structural ballast. They don't contribute to the charge, but they stabilize the nucleus. Too few and it falls apart, too many and it also falls apart, but more slowly. We'll get to that. Here's the problem nobody explains when they teach this. Protons all carry positive charge, and positive charges repel each other violently. Two protons brought close together push apart with enormous force. So how does the nucleus hold together at all? You've got dozens of positively charged protons packed into a space smaller than a housefly, and they should be blowing each other apart every microsecond. The answer is something called the strong nuclear force. It's not electromagnetism. It's not gravity. It's a completely separate force, the most powerful force in nature at short range. And almost nobody talks about it because it doesn't have a satisfying everyday analogy. The closest I can give you, imagine a grip that only works at arm's length. The moment you pull back even a few inches beyond that range, the grip vanishes completely. That's the strong force, incredibly powerful over extremely short distances, zero beyond them. The protons are packed close enough that this force overcomes the electromagnetic repulsion, just barely, just enough. My experiments, without my knowing it, were probing exactly that balance. When I measured the radiation coming off uranium, when I noticed that pitch blende emitted more radiation than the uranium content alone could account for. I was measuring nuclei that had lost that balance. I didn't know that yet. I knew something was happening. The numbers were too high. I went looking for the source. That's how polonium and radium were found. Not by predicting them, by following a measurement that didn't add up. Now the electrons, the part of the atom that isn't the nucleus. The model you were probably shown has electrons orbiting the nucleus, the way planets orbit the sun. Circular paths, fixed distances. It's clean, it's visual, it's completely wrong. Electrons don't orbit. They exist in what physicists call probability clouds, regions of space where the electron is more or less likely to be found, not where it is, but where it might be when something interacts with it. The electron doesn't have a fixed location. It has a probability distribution. The moment you measure the electron, the moment any particle interacts with it, you forced it into a specific state. Before that interaction, the question, where is the electron right now, doesn't have an answer. Not because we can't measure it precisely enough, because the answer doesn't exist yet. This is not philosophy. This is the measured behavior of real particles. It was being worked out mathematically in the 1920s, just as my own work was ending. I was at the threshold of it, watching matter behave in ways that defied the models we had, and I'll be honest, I found the uncertainty less disturbing than many of my colleagues did. I had been comfortable with not knowing for a long time. The measurements came first, the explanations followed later, or not at all. Radioactivity, let's say exactly what it is, because it's almost never explained correctly. It is not a coating. It's not contamination in the way rust is contamination. A radioactive atom is a nucleus with an imbalance. Too many neutrons, too few, some structural instability, and it's correcting that imbalance by ejecting something. 3 ways it does this. Alpha decay. The nucleus ejects a bundle of 2 protons and 2 neutrons together. That bundle is called an alpha particle. The nucleus loses mass, loses charge, becomes a different element. Uranium-238 undergoes alpha decay and becomes thorium-234, not uranium anymore, thorium. Beta decay. A neutron inside the nucleus converts into a proton, and the excess charge flies out as a high-speed electron. The element changes again. 1 more proton means a completely different atomic identity. The atom that existed a moment ago is gone. Something new is in its place. Gamma radiation is different. No particles ejected. No change in element. The nucleus drops from a higher energy state to a lower one, and that energy difference leaves as a pulse of electromagnetic radiation, pure energy, no mass. Uranium doesn't just decay once, it decays 14 times in a chain alpha beta alpha alpha more steps until it reaches lead, which is stable. Stable means the nucleus has found a balance it can keep. Lead sits there. It doesn't transform. Uranium, given enough time, becomes lead. Every atom. Eventually, what I was measuring in my laboratory was the energy released during these transformations. The ionization, the way radiation strips electrons from air molecules and makes the air conduct electricity. I built an electrometer sensitive enough to measure it. I measured uranium, thorium, my new elements. I got numbers, precise numbers, and I had no explanation for the mechanism producing them, because the mechanism wasn't understood yet. The half-life of carbon-14 is 5,730 years. Radium-226 is 1,600 years. Polonium-210, the element I named for my homeland, is 138 days. Same physics, wildly different time scales. We can calculate these rates with extraordinary precision. We still don't fully understand what determines them at the level of the individual nucleus. That question is still open. Which brings me to something that should genuinely bother you. We can tell you exactly what fraction of a radioactive sample will decay in the next hour. We can do that for any isotope, to many decimal places. What we cannot tell you, what nobody can tell you, not now, not ever according to current quantum mechanics, is which specific atom will decay next. I measured ionization rates to 4 decimal places. I could account for the behavior of trillions of atoms simultaneously with high accuracy. I could not tell you which individual atom would go first. That is not a technical limitation. Quantum mechanics says the individual decay event is genuinely undetermined until it occurs. The atom doesn't decay because some internal clock runs out. There's no hidden variable counting down. It decays because probabilistically at some moment it does. The precision and the ignorance live in the same equation. They are not in tension. They are both simply true. Whether this represents a fundamental limit to what can be known, or whether some deeper theory will one day explain individual events, that is genuinely unsettled. I would not predict the answer. Go deeper, because protons and neutrons are not the bottom. They're made of quarks, 3 quarks per proton, 3 per neutron, held together by particles called gluons. The quarks carry fractional charges. A proton's 3 quarks carry charges of +2/3, +2/3 and -1/3, which sum to exactly +1. Neutron quarks sum to 0. Here's the strange part. A quark has never been observed alone. When physicists try to pull one out of a proton by adding enough energy, that energy doesn't free the quark. It creates a new quark-antiquark pair. You get more quarks. You cannot isolate one. This is called confinement. And while we can describe it mathematically, we don't have a complete explanation for why it works this way. The mass problem is stranger still. 3 quarks account for roughly 1% of a proton's mass. The other 99% comes from the energy of the gluon field binding them, from the motion and interaction energy inside the proton, not from matter, from energy, structured into stability. When you hold a proton in your mind, understand that almost everything you're holding is not particles. It's bound energy that behaves like mass because of how it's organized. We don't know if quarks have an interior. They may be truly point-like, dimensionless, with a size of exactly 0. Or they may have structure we don't yet have instruments sensitive enough to detect. Every layer we've opened has revealed another layer beneath it. There's no guarantee the next layer doesn't exist. There's no guarantee it does. 4 forces govern all of this. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force. Inside the atom, gravity is not relevant. It's so weak at this scale that its contribution is unmeasurable, billions of times weaker than electromagnetism at the distances we're talking about. The structure of atoms is not gravitational. The weak nuclear force is what drives beta decay. It's the force that allows a neutron to convert into a proton, changing the identity of the element. It operates over distances even shorter than the strong force, and it's the reason radioactive transformation happens at all. These 4 forces are not unified. Physicists have spent over a century trying to write a single equation that describes all four under one framework. They have not done it. The Standard Model, our most tested, most successful theory of particle physics, accounts for 3 of the 4 forces with remarkable accuracy. Gravity is not in it, not because physicists forgot, because nobody has found a way to make quantum mechanics and general relativity compatible yet. The 2 most successful theories in the history of physics cannot be fully reconciled with each other. I was trained to believe the complete theory was findable. In this particular case, it has not yet been found. That is the current state of the measurement. My hands. Let me come back to my hands. I spent years in a converted shed in Paris, processing tons of pitch blended to isolate fractions of a gram of new elements. I stirred boiling radioactive liquid with an iron rod. I carried samples in my coat pockets. My notebooks, the ones from 1898 and after, are stored today in lead-lined boxes at the Bibliothèque Nationale de France. You must sign a liability waiver to view them. The paper itself is still radioactive. What I was doing without knowing it was sorting atoms by how urgently they were trying to become different atoms. Each radioactive element I isolated had its own characteristic rate of decay, its own signature. I read those signatures through their ionization effect on air, the atom's interior, the nucleus struggling towards stability, expressed itself through the air around my samples. I measured the expression. I didn't yet understand what was expressing it. The damage radiation did to my body came from the same mechanism. Alpha particles, beta particles, gamma rays carrying enough energy to knock electrons out of molecules in living tissue. That disrupts chemical bonds. It breaks DNA strands. The cell either repairs it, misrepairs it, or dies. I noticed my fingertips cracking and going numb. I noted it in my records. I attributed it to the chemical handling. I continued working. I was wrong about the cause. I was not wrong to continue working. The measurements needed to be made. Everything I've described, protons, neutrons, electrons, quarks, gluons, the 4 forces, accounts for approximately 5% of what exists in the universe. The remaining 95% is dark matter and dark energy. We call them that not because we understand them, but because we don't. The name is not a description. It's a placeholder written in the margin of a calculation that didn't add up. Dark matter doesn't interact with light. We can't see it directly. What we can see is its gravitational effect on galaxies, the way they rotate, the way light bends around them. The math only works if there's more mass than we can detect. So the mass is there, and we've never identified what it is. Dark energy is stranger. The universe is not just expanding, it's accelerating. Something is driving that acceleration. We call it dark energy because we have no better name and no mechanism. It comprises roughly 68% of everything that exists, and we have essentially no understanding of what it is. Every atom in your body, every proton that held together long enough, every electron cloud that made chemistry possible, every nucleus that participated in the reactions that built you, is a tiny piece of a universe that is mostly made of something we cannot yet examine. In 1898, I had a sample that glowed faintly in the dark. I did not know why. I wrote down the measurements and went back to work. That is still, as far as I can tell, the correct response.